Welcome back to the MATLAB tutorial series. In this lesson, we dive into one of the most powerful capabilities of MATLAB's Symbolic Toolbox, solving equations. From simple algebraic equations to advanced transcendental, integral, and differential equations, MATLAB can solve them symbolically or numerically. We'll also learn how to use graphs to choose good initial guesses and understand how MATLAB's VPA, variable precision arithmetic, helps find accurate solutions.
Before solving equations, we need symbolic variables. Using the command symsx, MATLAB treats x as a symbolic mathematical variable instead of a number. This allows us to build equations, rewrite them, and solve them exactly or numerically. Let's begin with a classic quadratic equation. X squared minus 4x plus 3 equals 0. We type EQ1 equals x squared minus 4 times x plus 3 equals 0. Solve EQ1, x. MATLAB returns the exact symbolic roots, in this case, the numbers 1 and 3. Symbolic solvers are great for algebra, calculus, and verifying textbook results. Now let's solve an equation that cannot be solved analytically. E to the negative x equals sine of x. Equations mixing exponentials and trigonometric functions usually don't have closed-form symbolic solutions. To solve it, we first rewrite it as f of x equals e to the negative x minus sine of x. Then graph it. F-plot of f from -5 to 10. Where the graph crosses the x-axis, we have approximate roots. These crossings give us initial guesses for numerical solving. Next, we use vpasolve. F equals 0, x, guess. We choose several different initial guesses based on the graph. Since each guess may lead to a different solution of the transcendental equation, we place these guesses into a list and loop through them using a for loop. Inside the loop, vpasolve computes one solution per guess. MATLAB stores each computed solution in a variable so we can display them all at the end. Now, what does VPA mean? It stands for Variable Precision Arithmetic, MATLAB's high-precision numerical engine. It allows MATLAB to compute solutions with accuracy beyond standard double precision. Using different guesses lets us find multiple solutions to the transcendental equation. Next, let's solve a differential equation with an initial condition. The derivative of y with respect to x plus y is equal to x, and the initial condition is y of 0 equals 1. In MATLAB, ODE equals diff of y with x plus y equals x. Cond equals y of 0 equals 1. Dsolve of ODE, cond. MATLAB returns the exact symbolic solution, perfect for control theory, modeling, physics, and more. Let's solve an integral equation. The integral from 0 to x of t squared with respect to t equals 4. Using MATLAB, EQ equals int of t squared, 0, x double equal to 4. Then solve EQ, x. MATLAB solves for x exactly, something that would normally take several algebraic steps by hand. MATLAB can also solve systems of equations easily. Consider x plus y equals 4 and x squared plus y squared equals 10. We type solve bracket x plus y equals 4, comma, x squared plus y squared equals 10, comma, bracket x comma y bracket bracket. MATLAB returns both solution pairs instantly. Let's recap what we learned today. We solved algebraic equations symbolically. We solved transcendental equations using graphs and vpasolve. We explained that VPA means variable precision arithmetic. We solved differential equations exactly using dsolve. We solved integral equations and systems of equations. MATLAB's Symbolic Toolbox turns complex mathematics into clear, manageable commands, making it an essential tool for engineers, mathematicians, and scientists. If you enjoyed this tutorial, don't forget to like, comment, and subscribe for more MATLAB lessons. Thanks for watching, and see you in the next video.